Today's topic, continuing in our sequence of soil orders, we're going down the taxonomic order, brings us to the warm and tropical destination that is Oxisols. Sharing, this is good, this is good. So I'm skipping ahead a little bit. Like I just said, we have our guest lecturer coming up for spodosols and andosols. Those technically key out first in the order that is soil taxonomy of the order that these soil orders go in. So we're skipping ahead a little bit to oxisols, but as these definitions are pretty narrow at the top, there's not a whole lot of conflict here. Like we covered gelsols already, and histosols, a little bit of overlap there, maybe whether they're really organic soils with permafrost or not is the key determining factor for gelsols. These oxisols are as different as it gets from the gelsols, at least. They're usually very old, very highly weathered soils found in tropical regions of the world. Very few weatherable minerals is the key for oxisols. If the mineral component of the soil can weather out, it probably already has in these oxisols. They're old and they're highly weathered. A lot of times these clay particles, specifically phyllosilicate clays, so we talked about those four groups of silicate minerals, and you can also watch our soil mineralogy lecture on Canvas. The phyllosilicate clays make up a lot of the cation exchange capacity, the nutrient exchange ability of the soil. So like the inherent soil fertility is what that means, is coming from these phyllosilicate clays, and the weathering out of silicate clays is what happens in oxisols. So kind of by definition, these oxisols are characterized by extremely low native fertility, high phosphorus retention by the oxide minerals that are there, low cation exchange capacity. So not very inherently productive soils. That's not to say that they don't grow a lot of things. That just requires a lot of inputs, lime and fertilizers, perhaps. So you can still use oxisols for agriculture. It's just a little more difficult. We've got 5 suborders. 7.5% of the global ice-free land area. That's kind of right in the middle of the distribution. For the globe, however, in the US, it's much, much less, and it's really only restricted to the tropical areas. So what this means around the world, it's Brazil, it's the Amazon rainforest, it's Central Africa rainforests. Oh, man. Come on. Okay, in the US, let's see if we can get around this. Yeah, that looks fine. We also don't see much of anything here like the gelsols. However, where you look for Alaska to see the gelsols, here you'd look for, they really don't even show up in Hawaii, but in Puerto Rico as well. So the tropical, the vacation destinations for our soil orders is where you got to go to see oxisols. This is a better representation of it. So Puerto Rico and Hawaii is where where we can find oxisols. They're really only on the older, the more western islands of Hawaii. And that is because a pretty steep climate gradient is observed across these islands. I still have not been to Hawaii. I would love to. This is probably where I'm hoping to see my first oxisol would be in Hawaii. But as I understand it, it's a pretty different. So each Hawaiian island is it's almost like a chronosequence, right? The Hawaiian Islands formed by a hotspot, the continental or the oceanic plate moving tectonically across this source of magma in the Earth's mantle that creates these islands as the plate is moving. So the youngest one is at the front, the oldest one is at the back. These oxisols, highly weathered soils, they take a long time to weather out. So it makes sense that they're located on the older islands. And then the difference in the green and the orange colors here for the suborders is based on the climate. More rain further to the west in the Eudox suborder. A representation of the soil of the oxisol suborders is really on that climate gradient. From the top to the bottom here, we have wet as in like saturated conditions. So the aqueous suborder, they have a water table at or near the surface for much of the year, similar to a lot of other orders when we have the aqueous suborder. On the bottom row is now like a wet to dry scale for the climate, like the moisture regime. So on the dry end on the left, toric, meaning like hot and dry, arid climate, oxisols, ustox and udox there for the soil moisture regimes. And then the parox would be the most precipitation, the highest annual precipitation, most humid climate, perhaps. This is a little interesting special moisture regime called the perudic, where precipitation exceeds evapotranspiration in all months. So usually there's a deficit range where you have the evapotranspiration, so the plant demand for water exceeds the supply, and then they're going to start to utilize the water stored in the soil profile. If that never happens, if precipitation is so high that it's always higher than what the plant demand is, you're in this perudic soil moisture regime, and you would have the parox suborder. Definitely like a tropical rainforest condition, and nothing we would see around here. Some oxisol profiles to look at. Let's start with this one. Maybe up to 40% of the total soil representation of Brazil. Haplustocks, so it's a very deep soil, bright red colors associated with hematite. So the iron oxide that's left behind when a lot of the silicate is weathering out, silicate leaves iron minerals behind, they develop into hematite, I should say, which gives it this red color. So not only is natural fertility really low in oxisols, but because of all these iron oxides, it sequesters a lot of phosphorus. So phosphorus retention is really strong. Phosphorus deficiencies observed in plants. And we have these BO horizon from the oxic materials, which is the weathering out of the silica and the weatherable minerals. Desilication would be the process going on here. BO horizons. Another example here with a different iron oxide called goethite rather than the hematite gives it this yellow color. Usually when we see these big differences in mineralogy and color, we would say it's a much different paramaterial. This is clearly formed out of a different rock type or something. But really, these two could have started with a very similar paramaterials, and this iron oxide formation is really a factor of the environment. So this yellow goethite mineral forms in relatively more acidic, cooler, and wetter places than the red colored hematite does. So iron is released through the weathering of these silicate minerals, and that's why this one looks a lot more yellow than the other red one is, but it still has the same horizonation, AP horizon, over these BO oxic layers. Then in the aqueous, so similar to all the other ones, with glaying going on here, not a whole lot of iron present to give it the red or the yellow hematite or goethite forms. But the minerals that are remaining here are still very highly weathered. Very few weatherable materials remain. But the glaying conditions, the saturated, the iron reduction, and depletion perhaps gives it the gray color like we see a lot of other ones. So rather than the BO horizons, we'd go with BG. And to classify it as the oxisol, you'd have to know a little something about the mineral components themselves. Otherwise, this would be hard to recognize just from a photo, perhaps, if you didn't know it was from Brazil or from a tropical rainforest or really an old paramaterial and landscape. It would be hard to tell based on horizonation that this is an oxisol. But the aqueous, it can still be an aqueous condition, still have the reduced forms. Drainage is not necessarily required. Thorax now on the drier side. This is landscape view of a pineapple growing operation, pineapple field here. You can still, let's see, 25 inches of annual precipitation, which is about what we have here in Moscow. Much, much hotter average temperature. Much of the weathering associated with these soils took place under more humid conditions in the past, so changing climate over time requires irrigation and fertilizers too for production. Profile here, eutotorox. More intense weathering, BO1 and BO2 horizons. Hematite is the mineral here that gives it the bright red color. Molokai series. So this is a familiar one, perhaps. We have the one Oxisol monolith in our collection is from this agricultural experiment station, I think, in Hawaii of the Molokai series. So characterized by kaolinite clay as well. As far as I know, there's not really a specific texture that matches up with oxisols. You'd think the weathering out of the clay minerals would, or the phyllosilica clays at least, would make them really sandy soils. But the iron oxides themselves are behave like clays. They're clay size, right? Clay, the way we consider it for soil, this texture description is not a specific ingredient, but rather just the size of a particle. So these iron oxides might texture out like clays, or there can be a lot of kaolinite clay in the first place. That 1-to-1 gives clay, or it gives a different feeling. It's not as sticky, in my opinion, as most of the other, like the spectites, the 2-to-1 clays that we have. Most of the other polluce in our upland soils. Kaolinite is a little bit different. But because it's really old, highly weathered, common in these oxisols and ultisol environments. And so this is a magnification now, a thin section showing these well-structured aggregates. So the bright red color here is like a soil. You think of the soil aggregates. The dark red is the void space behind it, and then the bright white spots are what remains of silica. So if you did a zoomed-in view on any one of our normal soils around here, normal to us, it would be most of the white silica material and only very little of the red spots of iron, probably in an iron concentration. But in an oxisol thin section, it dominates. So stable aggregates are responsible for a lot of infiltration and permeability. So one strength perhaps of oxisol cultivation would be resistant to runoff and erosion. Dark areas are pore space, white areas are the quartz grains. I find myself really fascinated by this whole field is called soil micromorphology. So our skills in the pedology class are the texture, the color, the structure, the soil properties that we can see and describe with our hands and our eyes in the field. There's a whole subfield within pedology of micromorphology. So putting soil under a microscope like this and describing the features of it. And my dream would be one day to make this into a class and to learn about what these minerals are and what they look like and what they mean for soil management and research and what you can learn about a soil profile, as well as going out and collecting thin sections like this, bring them in and identify the minerals in them. I think that would be fun. So that's on my list of one day, maybe making a class for soil micromorphology, but not yet. Parox now, so the really wet ones. In the Hawaiian Islands, still acroparox, which is a wild or a very, very different taxonomic classification than we could arrive at around here. Still PO horizon, so nothing particularly spectacular or tremendous. Relatively high organic matter in this one, though. It looks kind of brown compared to all the other oxisols. Maybe an abundance of moisture is reducing some of the decomposition or facilitating the accumulation of organic matter in some of these profiles. Agricultural research station here, over 100 inches of rain per year. Pretty crazy to imagine. Rainfall greater than evapotranspiration every single month of the year. Perudic soil moisture regime, severely limiting these soils for agricultural production. It's just so wet there all the time. Hawaii gets, in one of these rainforests, the most rain of anywhere in the US. which would have a pretty dramatic effect on the soil formation there. And plinthite now, we talked about this for the BV horizon. Red, yellow slash gray or white mottled appearance. You can see some of these in the monoliths. I think plinthite, a BV horizon would be the best subordinate distinction for the kaolinite paleosol that we saw in Beauville. But these are like the current, the contemporary modern day plinthite profiles. Repeated wetting and drying, especially if it's like dries in the sun, irreversibly hardens into petroplinthite or ironstone, which we mentioned before can be used as a building material in a place where you can't really quarry the bedrock. Making whole entire buildings, walls, or fences out of this. This is a fort in Malaysia. Maybe weathering a little bit, not quite holding up to the elements. It is soil after all. However, over 500 years since this building was constructed. Not bad for something made out of soil, in my opinion. So that is plinthite, kind of a unique feature of oxisols or maybe ultisols as well. And then now some land use considerations. In Africa, a eudox landscape, shifting cultivation practices for low nutrient oxisols is a big environmental, global land management topic. You could say we know these oxisols have low inherent fertility, so in order to grow enough food and produce to for a lot of these really subsistence farmers, really small scale agricultural operations, it's a lot of slash and burn. So developing new land into agriculture, usually burning it to return biomass, mineralized biomass into the soil, return organic matter to the soil, and any amount of nutrients that comes with it. And then get a few productive years out of it, maybe 4 or 5 at the most, and then you probably have to leave it fallow, let it return to some kind of forest for maybe 10 to 15 years only to cultivate it again. So not a tremendously sustainable practice. Burning vegetation, leaving ashes in the soil, return some amount of nutrients, rotate crops through as best you can to give it some rehabilitation. Some of them, however, some of these oxisols might contain a lot of organic matter. This is at a high elevation in Rwanda. Humid tropics, you might contain more organic matter than you expect because the decomposition is restricted. You're able to accumulate organic matter, and you still have some of this nutrient exchange capacity, a CEC, appreciable CEC capacity. Some of these locations in high elevation in Africa support really high density populations because they're able to produce, they're able to farm these oxisols and support quite a bit. Maize, bananas, peanuts, perhaps in a system there in Rwanda with all this organic matter. Places that so in order to add organic matter to some of these oxisols, there's a really famous example of the Amazonian dark earth in Brazil. Terra preta is what this is commonly known as. Oxisols or ultisols dominated landscapes of Brazil. Really just this terra preta is an artificial material made of charcoal, other waste products, and they're like burned or put in a kiln together, and repeated additions over hundreds to maybe thousands of years, dating back a really long time, have added a lot of nutrients, organic matter, mineral, like essential plant nutrients to the soil, with a pretty dramatic difference between soils that receive this amendment and soils that have not. I have some pictures of this we can compare, as well as some limited personal experience with these kind of systems. So to review at least the important factors for ultisols, everything's listed on the webpage there. Takeaways are the central concept for all oxisols: tropical, highly weathered. If it can weather out of soil, it probably has, which is usually we refer to the silica minerals like that. We got those 5 suborders, mostly determined by the climate conditions. how to find them on the map, look for the vacation destinations. It'd be Hawaii, it'd be Puerto Rico, it'd be near the equator. Otherwise, common horizons and processes would be the desilication and the BO, usually multiple of them in a profile for our oxisols. Land use limitations then would definitely be agriculture on their inherent characteristics alone. Slash and burn or adding fertilizer are probably requirements for getting a lot of productivity out of these oxisols. The experience that I have with these, I lived through my brother's experience. I mentioned before he was a Peace Corps volunteer in Togo in Africa. I am the soil scientist of the family, and he joined the Peace Corps for his professional experience because he wants to work in an embassy in the future, be like a diplomat, and Peace Corps was his first step in that direction. But he had no prior experience with soil. He was deployed into the Peace Corps and their Peace Corps agriculture program to try to promote sustainable agricultural practices, because a lot of these farmers, or these fields at least that he and his coworkers observed, they get cleared out, they're under heavy production for a few years while the productivity lasts, and then they're just left fallow when they can't get a crop out of them anymore. And some of the Peace Corps agriculture programs was to add cover cropping or intercropping of legumes. So mucuna is the crop that they were using. It is this leguminous crop here that will add that adds nitrogen to the soil through biological nitrogen fixation. So I'm not sure how familiar he was in the first place with a lot of these plants or agronomic practices, but he learned all about them, and with my help as best I could to try to educate the farmers and the land managers of Togo about this. But they were really interested because a plant that provides its own fertilizer is the way they described it to the growers. And I was really excited to learn about this, to see some of his fields while we were there. My sister and I went to visit him over winter break a couple years ago, and this was very interesting to see. We saw pineapple fields, and some mucuna was still growing. We were kind of out of the main season for mucuna. It was December when we went, but in their dry season, but still like stifling humidity. I was not prepared. It was very cool to see these growing. Mucuna and manioc too are two separate crops that they grow. To see them used in these fields, successfully intercropping and being made into new products and food sources for these communities. I forget. I think these two are the mucuna plants, and this one is the manioc, maybe, or they're all the same. One of the other crops we observed, crops, or at least something they were doing, was harvesting these palm trees for the sap. Is anybody familiar with what the palm, could be palm oil, or also this palm sap is fermented into palm wine. Like they're cheap, local, easy source of alcohol that they ferment at home and turn into, it's called soda bee, and it's gross. It tastes so bad. Our brother was taking us around to introduce us to all of his coworkers and his the people he lives with in his village. He took us to the city hall to meet the mayor, and the mayor was so thrilled to meet us and was so honored to host us for a visit that he cracks open his office drawer and pulls out his finest bottle of soda bee, and this stuff is just nasty. My brother brought some home. That was a hit at his parties in grad school since he got back. But yeah, pretty gross stuff. The little holes that they placed their jugs in, though, was the closest I came to getting a soil profile, collecting some soil samples of this possible oxisol. I never was able to confirm it because I never actually made it home with these soil samples. Airport security made sure of that. But you just have to imagine, you have to feel sorry for me too. Imagine how hot and humid it must have been for me to get there, this place in Africa that I've never been to, probably will never make it to again in the future, and say, you know what? As excited as I was to dig and describe a soil pit here, I think I'm good. I think it's too hot. I think it's too humid. Let's just sit inside for this afternoon. And that was December. That was pretty crazy how wild the climate was. I did see a couple soil profiles though. Not totally sure what to make of these. This is an urban soil profile in a market site in one of the more developed cities that they were in. Lots of different fill materials, I think, and a lot of human artifacts, plastic debris and litter probably in some of these. But I could at least do a quick horizonation there. This is the one my brother was most excited to show me. It was just a little hole outside one of the restaurants in town. And I brought my tape measure and I brought a little bit of soil description equipment, not a whole lot. But I hopped in there as soon as we got there on the tour, and I wasn't really sure what to make of it. I don't know if this is maybe a plintite ironstone. It was really hard, this whole layer here at about 2 feet deep. But not a whole lot of tremendous horizonation to work with in a lot of these oxisol profiles. Could be ironstone, could be just really compacted, clay rich. Wasn't really sure what to ever make of that, but I will count it at least as a profile. Lastly, before we go, terra preta, organic rich anthropogenic soils. This is really the precursor to biochar. I'm doing my dissertation research in effects of biochar amendments on soil. Area of increasing research interest in soil science. Easy to say, was discovered by the Europeans maybe 20 years ago. Christopher Columbus style, though. The Amazonians were using biochar and terra preta much longer. So however they can get organic matter in the oxisols, they will take it. Thank you, everybody. See you back here on Thursday. Lecture with Paul Tietz.